Welcome to the fractional distillation tutorial. In this tutorial, I'm going to try and explain to you how we separate a mixture of several liquids. Let's create an imaginary liquid in this test tube, which I'm showing the molecules of it. Let's say that we have a solution, which means that this is homogeneous. It's evenly mixed throughout. The molecules have mixed themselves because they're attracted to each other. And we've got three different particles in there. We've got blue ones, we've got red ones, and we have green ones. And let's say that particle that is blue has a boiling point of 50 degrees Celsius. And the red particle, let's say, has a boiling point of 70 degrees Celsius. And we'll say the green has a boiling point of 90. I'm just making these liquids up. And they're mixed together and they form a solution, and there's no good way to get them apart except to boil the whole thing slowly so that each liquid boils away at its own boiling temperature. Now, in the real world, this doesn't happen as perfectly as you might hope because there's always some attraction between different particles. So, for example, the blue particles and the red particles are going to have some attraction to each other, and the red and the green are going to have some attraction to each other, and even the blue and the green. And so because of that, this is not going to give you a 100% pure substance the first time through. Usually you do fractional distillation a bunch of times in order to further purify your liquids. But for our purposes, we don't need to get that pure, so we're just trying to explore the way that this works. Here's what you do. So you just take your alcohol burner and you heat your test tube at an angle about 30 degrees tilted, and you have one of those stoppers that has two holes in it right here, a two-holed stopper, and through one hole you're going to put a temperature probe, which is on the left-hand side, and the little squiggly black line is going off to your LabQuest. And then on the other side you have one of those glass bends that comes through and then is attached to some white tubing. And what happens is, as you heat this up, the blue particles have very little attraction for each other. That's why they boil at such a low temperature. So when the temperature hits 50 degrees, they'll have enough energy that they can actually break apart from the liquid state and turn to a gas. And when they do that, they're actually going to move up to the top of the test tube because they move around more freely now, they're a gas. And so they'll eventually make their way into this tube, the glass tube. When they get far enough away from the heat, they'll start to cool off again, and when they cool off, they'll slow down and they'll come closer together, and you'll start to see, probably right around here in the glass bend, that your blue particles will start to condense back into a liquid. And what this looks like in the lab is it looks like a little bit of liquid is hovering in here, sort of appearing and disappearing. That's your gas turning back to a liquid. It was invisible on its way up the test tube because it was a gas, but by the time it gets right here, it's starting to recondense because the particles slow down and now their attraction overtakes and they get closer together. That's exactly what we want to have happen. We want this gas to escape from the mixture down here, the blue particles, but we don't want it to leave and just go flying into the air, so that's why we've trapped it with this device. So those particles will then turn to a liquid and travel down the tube, and what we do is we put this whole thing in an ice water bath down here. This keeps our liquid nice and cool so it doesn't re-evaporate for any reason. And what we do is we slowly collect those blue particles down here. And like I said, they might drag a red with them every once in a while because they're attracted to the red particles and they might be able to pull them out. But for the most part, you're going to get the blue liquid. Now, it may not be blue in color. I'm just using blue to represent the different particles so you can distinguish them. Now, I'll know that I'm getting my blue liquid when my temperature hits a plateau. That's why we hook this up to a LabQuest. Remember, we have this little wire going off to the LabQuest. Because what we want to do is we want to watch for the temperature to plateau and stay the same for a while. That indicates to us that, hey, we're getting a state change. That's why temperatures plateau. Because remember, the blue particles, when they go through a state change, need to use the energy to pull apart instead of speed up, because you can only do one or the other if you're a particle. Either you're speeding up or you're changing position. You're not doing both. So the blue particles are going to change position at 50 degrees. But when all the blue particles are done evaporating, now the heat energy that we're getting from the alcohol burner is going to go into speeding up the particles again. So we'll see the temperature shoot up when all the blue particles are gone. As soon as we see that, what we want to do is we want to remove this tube, and we want to put it in a second test tube. So you can just, this one will have to be clamped down, clamped into place, because otherwise it's an empty test tube and it'll float in the water. So you'll have to clamp it in place. So you'll probably have to pull this guy out when you're done, when your plateau breaks. You'll pull this guy out, put him in a test tube rack, and put a fresh test tube in there so that you can collect the second liquid. So with a fresh test tube, I'm just going to draw a second one because I can't erase with this program. Sometimes drives me a little bit crazy that I can't erase, but that's all right. Here's a second test tube. We'll just put them next door for the time being. And what you do is you just move your tube into it. And now the red liquid will move up as it turns to a gas. Appearing here, getting into the tube. It'll drip down also. Drip down, and you'll collect the red liquid at 70 degrees during that plateau. And again, it might drag some green with it. There might be some blue that was left behind. It's not 100% perfect. And the thing is, after our plateau breaks this time, we don't need to change tubes anymore because all we'll have is the green liquid left behind in here, which is awesome. That's what we want. We wanted these 3 different liquids to be separated. So it's a pretty simple process. Now, there are some tricks to it that we have to talk about for when we actually do it. The liquid that we're going to fractionally distill is cherry Coke, which is quite flavorful, but please, we cannot drink it because it is a lab activity, and we don't drink or eat any of the substances that we use in our lab for safety reasons. Your cherry Coke has a lot of things dissolved in it. It's basically a mixture of water as the solvent, carbon dioxide gas, which is what gives it that bubbly, fizzy feeling and that tingle on your tongue, sugar in the form of high fructose corn syrup, so it's a liquidy, syrupy form of sugar, some food coloring of different types of coloring, and some cherry flavoring. So each of those things has a different boiling temperature, and each part can be boiled away at a separate time. Your gas, your carbon dioxide gas, is already boiled away. It just is dissolved. You can have a gas stay dissolved in a liquid as long as you keep your liquid cool. As soon as you start warming your soda up, you'll see that your carbon dioxide will bubble right out of it. And this should make sense to you because if you think about it, if you look over here on the right-hand side, if these are particles of a liquid, let's say, and when the liquid is cold, they're pretty close together, those particles. Not right on top of each other like a solid, but they're pretty close together. So let's say I have this pink carbon dioxide gas that's dissolved in it. Well, gases are less dense than liquids, so those red particles have a tendency to float up and try and escape the liquid. But if the particles, those black particles, are close together, they tend to force the red particles to stay in solution because there's not a lot of room for them to escape. They start to move around and they keep bumping into black particles. On the other hand, if I heat the same liquid up and the particles get a lot further apart, well, now a carbon dioxide molecule has sort of almost a clear shot right out of solution. This is why gases are less soluble as you heat up your solvent, but that's not true of solid solutes. So our gas, our carbon dioxide gas, will bubble out pretty quickly as we heat it. The other thing that's going to come out really fast is the cherry flavoring. If you think about it, for something to give flavor to something else, it has to have a strong smell, because really your sense of smell and your sense of taste are strongly related. That's why nothing tastes very good when you have a cold, because your sense of smell is compromised. What you're smelling are particles that actually get into your nose, and that means that in order to smell something, it has to turn to a gas. This is why water doesn't feel like it has much of a smell to us. It does, but it tends not to be in the air in large quantities, because it doesn't boil away very easily. On the other hand, cherry flavoring jumps right into the air. It is a liquid, but it just as soon as it gets a chance, it turns right to a gas. And that's why you can smell that strong cherry smell from your cherry Coke. So just like the carbon dioxide gas, our cherry flavoring also is going to pop out pretty quickly. So we're not going to have very much cherry flavoring or very much carbon dioxide. They're a small part of your soda mixture. It's mostly water and sugar. So we can't really collect our carbon dioxide and our cherry flavoring in separate test tubes. Instead, what we're going to do is we're going to heat gently, and we're going to hold this tube up by our nose. Now, not in our nostril, but in front of our nose, about 2 inches away from your nose, and you're going to waft the smells coming out of the end of the tube gently towards your nose as you first begin heating. What you're doing is you're waiting to see, when do you smell cherry flavoring. When you smell it, you're going to record the temperature you've got on your LabQuest. That'll all be set up for you already. So when you smell that temperature, you're going to call that your plateau temperature for your cherry flavoring. That plateau is going to happen really fast because there's so little cherry flavoring that it's all going to come out pretty much at once, so you're not going to get a nice plateau temperature. So this is how we're going to get around that. We're just going to smell it. As soon as you feel you've smelled the cherry flavoring come out of your tube, you're going to then start collecting your carbon dioxide gas, which is also bubbling off pretty quickly. When you do that, what you want is to, instead of collecting the gas, because you'll only get like a fingernail's worth of carbon dioxide gas out of this tiny amount of cherry Coke, we're only doing 5 milliliters, instead of actually collecting it, we're just going to check for its presence by using an indicator solution. So what you'll do is you'll put that tube into a test tube that you have clamped to your pegboard. And in that test tube, you're going to put a purplish looking liquid, which is actually made from red cabbage. And red cabbage is what we call an indicator. It's like that phenolphthalein stuff that we used on our baking soda. It turned pink when it hit an acid. It turned white when it hit a base. Or maybe it was the other way around. I always get confused with that. But this indicator changes colors also when the pH changes. And carbon dioxide will make something turn to an acid. So what we're going to do is we're going to have the end of this white tube in there. And as the carbon dioxide gas bubbles through, you should notice a color change in your cabbage juice. Cabbage juice smells terrible, just letting you know right now. And as that color changes and the temperature goes up, you're going to keep an eye on it. When you hit about 60 degrees, you're done. You can take that tube out, and now you can put it into your first empty test tube to collect your first actual liquid that we're going to hold on to. And this liquid is going to be water, so it should boil around, but certainly not exactly at 100 degrees Celsius. So you should get a nice plateau at around 100 degrees, and you should start to see a clear, colorless liquid, that would be your water, forming down here. After that plateau breaks significantly, meaning it goes up about 3 degrees, that's when you are sure that all your water has boiled away. But you have to be careful. You got to keep your eye on what's left. What's left is basically sugar in a syrup form and some food coloring. It will burn if you heat it over much. So what you want to do is you want to get this balancing act between getting all your water out and not burning your sugar. Ideally, you want your sugar to be left in here in a syrupy form that isn't burned, excuse me, so that you'll be able to get its density and run some tests on it. If you burn it, you won't be able to do that. And it's pretty easy to make sure that your water comes off okay. But again, it's hard sometimes to know, hey, should I stop heating my sugar or shouldn't I? You should stop heating your sugar if any of the following happen. Like I said, if you go up by 3 degrees in temperature from whatever your boiling plateau was, definitely stop then. You should stop heating it if it looks to you or smells to you like it's starting to burn. Definitely stop heating it then. Or if you notice that you're running really, really, really low on liquid. If it's just like maybe a milliliter of liquid left, good enough. Stop, because you're close. Now, when you are ready to stop heating your cherry Coke, don't blow the flame out before taking this tube out. Whoa, I hate when I do that. It's so annoying. Okay. You want to pull this white tube out of your test tube before you blow out your flame, and then you can just drape it over the edge of your pegboard. The reason you want to do that is because as soon as you blow out this flame, the molecules of gas in this test tube are going to slow down because they're suddenly going to lose all that heat energy. When they do that, they're going to exert less pressure inside that test tube, and it's going to create a partial vacuum, which will suck anything that's in here back into here, totally undoing what you just spent all that time doing. That's called suck back. We've talked about it before. You don't want that to happen. It ruins your experiment. So make sure you remove your white tube before you blow out your flame. After you blow out your flame, you can just let everything kind of sit and chill for a while, get down to a nice temperature, and work on other parts of the lab in the interim. Now, you have to read the lab sheets carefully because they give you other important specific instructions that you need to be careful of, including, you see these little white chips here? These are called boiling stones, and they are used to prevent the liquid from boiling too violently in the test tube. What happens is if you just try and boil a small amount of liquid in this test tube without them, the liquid will start to bubble so vigorously that it'll actually knock your test tube right out of your clamp. And if that happens, by the way, don't try and catch it. It will be hot. Just let it go. I promise you, I can clean up the glass a lot easier than I can clean up your burnt hand. So these little guys, if you put them in there, they collect bubbles on their surface, and that prevents the knocking of your test tube, which is much, much safer. So there's a lot of little things like that that you need to pay attention to in your lab sheets. And then we'll do the lab. I'll see you guys in class.